Good morning, everybody, and welcome to our MSC Apex Generative Design Release webinar. I am Thomas, and I have Anne with me in her flat, of course, so doing all of this in the home office remote system. I hope everything will work, and I would like to welcome you today over here. We will give you a short introduction in our software system into the mindset, what's behind, what do we think about generative design and how to use it, and we'll give you a glance on this specific software. I hope this will be as interesting as you has expected it. And if you have any questions, please write them into the chat and we will answer them in the end of everything. So let us start. What you can see over here is just a nice video of a simple part that we have generated with MSC Apex Generative Design. What we can see is a very simple bracket that looks very organic shaped. This is a bracket from an aerospace plane, and we have done an optimization on it. So beforehand, it has been made of two different sheet-like metal parts that have been milled and then attached to each other and then to the primary structure. We have done an optimization on it to come to one single part that can be 3D printed, and that has about 60% weight reduction. We have gained this weight reduction because we have done this optimization on the overall structure, have rethought the idea of the product, so how is the design made, and by that reduced the fixation points and come from two different parts to one integrated part design. So we have found a very new design, even a new concept of this assembly with using our software, and all of this in a very short time of just 2.5 hours calculation time. We have done several iterations, several optimizations to find the very perfect part design that fits to all of our other needs that we cannot cover inside the optimization. But in the end, we have found this design, what is very durable and that much more lightweight. As well, it saves a lot of time and money in the assembling phase because now we have these 4 fixation points directly towards the primary structure and saved around, I don't really know, 5 or 6 more fixation points towards each other of the 2 parts before and towards the primary structure. And this is what we want to do. We want to enhance products to get to better products in short time, save money, save time, save resources. So I would like to start with putting all of this new ideas, this new design technology into some context. So Ralf Sundermeier, the head of CAE methods from Volkswagen, just said in last autumn that he thinks in 2025 virtual computation is used at every engineer's workstation. In the same topic, CAE processes must be operable without special expertise. Of course, this goes hand in hand because nowadays the CAE engineers are very high specialized people that are working in their specific areas, and it is not something that's used at every engineer's workstation. So there's of course the task for the engineers to be open to use these new technologies. But on the other hand, there's a task for the software providers to get the software that is usable for everybody. And this is what we are aiming at. We want to have the software usable for every engineer as easy as possible to go this way of putting CAE into each workstation and by that into each part that has been designed. This comes as well to the expected transformation of the market inside the next 20 years, where we can see on the left side 2019, where we do have a lot of big bubbles in the real world, the upper left side, like extrusion, stamping, casting, molding, and just small bubbles in the digital world on the right side. But on the right side, in 2030, we expect to grow the 3D printing industry massively, the digital twin that's not even covered on the left side, and the generative design that is not covered on the left side. Oh, it is very small, but this will grow as well. So we see that fitting to what Ralf Sundermeier said, we expect to get a lot more digital in the next 12, 20 years. But this might change as well, because you know that due to the current situation, a lot of people are working from home. Things are digitalized that we did not expect before. And we think that this will get faster as well. But in the end, we expect this generative design market to grow fast in the next years, because new tools are arising, like our MSC Apex Generative Design, and they are getting better and more connected to the real world, so that they really are giving benefit to the designers. We talk about CAE, generative design, etc. I think many people will think directly about optimization of structures. And there we all should know the topology optimization technology. Topology optimization is quite a good technology based on finite element methods, where you start with a big block of design, put your loads on it, constraints, and then the overall block is calculated. And those elements that don't have big stresses or strains, or that do not have a big influence on the overall part performance, are thrown out step by step. And iteratively, a thin structure is generated. The problem with this topology optimization that is based on this finite element exactly and directly is that you often get some unclear results, as seen in the 4 pictures above. Discontinuous connections, problems with resolutions, because you have to start with one resolution at the beginning, and a lot of disgusting work comes in. As well, if you have a look at the overall process chain below there, starting with mesh generation, setting up constraints, do the optimization, interpret the results, and then redesign everything, adjust it, smooth it, get to a CAD system again, and then get to the verification. This is a lot of work. So topology optimization is a nice idea, but it's not the final solution, because this is something that can be done by CAE experts, and it takes a lot of time. We thought we need to have something different to get CAE and optimized parts at every engineer's workstation. So we want to get as clever as the nature. If we have a look at this tree, you see that the tree is very stable in the ground. You know the trees don't move normally, but above you see that the branches are getting thinner, and they are perfectly adapted to the surrounding environment. So as well, this tree can handle all of the loads that are coming, like wind loads or rain and snow, but as well, it just uses material exactly where it is needed. So nature is very good in saving resources. And we want to get as perfect designs as this. But there is a problem. We need to manufacture these designs as well. This is where additive manufacturing comes in, because additive manufacturing is capable of designing very complex parts, not over old airplanes like over here, but smaller things like turbochargers, brackets, whatever. A lot of things are possible to be manufactured additively nowadays. And with additive manufacturing, we could go for such complex designs like the tree, so real nature, bionic looking shapes. But we have to design it, and there topology optimization might be a solution, but it's not, because it's very lengthy, complex, and expert knowledge is required. Well, in the end, the CAD systems are not capable of handling this. So we need to get a new solution, and this is what MSC Apex Generative Design does, because we rethink the existing. We are not going for a high accurate finite element analysis, but concentrating on the DFAM, so the design for additive manufacturing core. Like if you have a look at this boarding passes down there for the aircraft. On the left side, you see the normal boarding passes that all of us know. A lot of things are standing there, and you don't really figure out what is the information that you need for getting onto your plane. On the right side, you see the same information, but it's very easy to understand for a human where he's flying from and to, which gate he needs, etc., etc. Everything is there, very easy. And as well, you still have the barcode over there, so it's still machine readable. So why don't we take these very easy to use boarding passes made for the users and not for the machines? So we think that you have to concentrate on this, develop lean processes that are customer focused, and keep it simple. And this is what we've done with the optimization process and with, in the background somewhere, topology optimization. We have seen this existing workflow, and we have made this short one out of it. This is MSC Apex Generative Design, where you just set up your constraints and goals very easily in a very intuitive user interface. Just work on geometrical things. You set up your model as you think about the model and not as the mathematic background is needed. And then the rest is completely automated and running through in one software. Automated mesh generation, automated smoothing, retransition, and even verification can be automated. This is what we think is the right way to keep an eye on the user and to develop the software for the user, not for the mathematics behind. We are going to integrate this optimization solution into the big MSC portfolio of software and simulation processes. So you might know the other technologies from MSC like Adams for multi-body simulation, the normal Apex structure and simulation for setting up models, simulation, etc. Then we have the generative design, and we will combine all of these together so you can get from the beginning the loads from Adams, run in generative design, get it to Nastran for validation. It's a high accurate FE solver, and as well go for Digimat or SimiFact Additive for running the process simulation of the plastics and metal additive manufacturing. Not all of this is ready right now, but this is where we want to go. This is our goal, and it will be there quite soon. As well, if you go on this path, if you're running this generative design, you can save a lot of money. I think this is most important for most companies. Save money. Of course, get better products. This is what you will have as well. But better products can save money. And this is what we are doing because our solution is very fast. You can go for a lot of optimizations in a short time frame and get perfect designs. As well, it's quite automated. So fast and automation comes hand in hand, of course, but you can run all of this very smoothly. What you get out is not just lightweight. This is the main purpose of a design optimization for saving weight. But what you get is as well new ideas. You get new products, you can test new things, as we have seen in the very beginning for the first bracket, where we have come from two different parts that have been mounted together and then to the primary structure. So it's a very simple part, but yes, we have changed it from this complex thing with a lot of assembling work to one part design that is mounted with 4 screws, and that's everything. So new ideas with lightweight designs. And finally, we say you get new technology access with the software. Because if you want to use additive manufacturing with all its wonderful design freedom and all the new things that you can do, you need to have the right engineers who are able to do that. And if you are an engineer, you need to set up all this knowledge for additive manufacturing. This is quite a lot of work, and you should get help by our software. So you run the optimization, and what's coming out is directly something that is mostly very easy to print, and you can take the software as a perfect assistant to your daily work to get to better designs in shorter time frame. And you might even take another coffee while the system is running, and you're coming back and your work is done. As well, a big topic, we think variety is a key for successful designs. In the picture below, success is never a straight process. You always have to look at different solutions. This is what designers are doing every day. They are not just drawing one part, manufacture it and say it's perfect. No, they think about it. They think about different ways how it can be designed, and different methodologies how the overall product could work. And this is something that we assist in as well. Because like for this very simple part, just a bookshelf or something, it's mounted to the wall behind and some loads coming from above. We can generate thousands of different designs that all meet the same requirements. All of them see the same loads, the same constraints. They might have different weights, but all of them meet as well the stress constraints. So all of them will withstand the loads. And the important point now is that we can assist this with our software and get to the different designs with just changing very few parameters. So I think 2 or 3, that's all. And you can get to all of these different designs. And then you can decide on which of these designs is really fitting your needs. And this is far beyond just the structural side of carrying loads. Designs are always as well keeping into account the environment, like dirty environment. Your part needs to be cleanable very easily. Or some temperature problems. Do you need a big surface? Or do you don't want to have a big surface? Or you have to be in a clean environment, like for medicine or food industries. So you just want to have a not that complex part. All of this is something is very complicated to teach the software. No worries, the software just will give you out different designs, and then you decide which one is fitting all of your secondary constraints and demands on the parts. So the software is generating hundreds and in the background, thousands of different designs. And then they go through something we call design funnel. First step is it's always looking on if the stresses are met. So will the part withstand the loads? It's trying to take the most lightweight designs because saving material is saving costs, is better for our nature. So if we want to copy the nature, with its intelligence of producing parts, we should take care for the nature as well. So saving materials, saving resources is good. Then we have this design point, like aesthetics or other things like dirty environment, etc. And in the end, we need to cover the manufacturing aspect as well. This is where we say, take your design candidate, the results of the optimization, and throw them into Digimet for plastics or semi-effect additive for metals into the manufacturing process simulation. And in the end, you are coming out with your design that is perfectly fitting all your needs, including weight, designs, manufacturing, and of course, stresses. If we want to go for so many different designs, we need to increase efficiency. Less effort, more speed. This is efficiency, and this is where the good designs come from to get to feasible overall process. So we have designed new software for new design era. What we mean by this is that we have changed a lot of things that are behind it. As I said in the beginning, topology optimization is the idea that is lying behind. And this is based on highly accurate finite element simulation. What we have done was setting up our generative design engine in behind is that we have overthought those things that are behind the finite element method and the topology optimization, developed completely new optimization method, something that was not there before, that is quite fast and perfectly adapted to additive manufacturing, to what we want. And all of this based on some assumptions inside the simulation to have a perfect trade-off between accuracy and speed. So we are very fast, doing some things very different than before, but with this change, we are getting to the high efficiency that is needed for our customers. And all of this now covered in the MSC Apex environment. So very easy to use, easy to learn software environment. and surface. So you can easily set up your model based on the CAD geometries and don't care about the finite element details, but just go for the geometrical things. Set up your model as you think the model is behaving in the real world, and then let the software do everything in the background. Don't care about, you're just getting out your final designs. If you talk efficiency and saving material, talking about costs is of course important. In the end, cost is everything. So we go for automation, going for lightweighting, and by that, going for time reduction. So 3 things combined with each other, taking different designs, having lightweight designs, this automated, everything fast in the model setup and the solution time. And in the end, by this, we will make this nice pig happy because we can save a lot of money, a lot of time. This is where we can go. And then finally, I want to talk about some nice puppies. Talk about from data to creativity, intelligent software. It's a nice marketing frame, but there's something behind. Because if you look on the left side down there, we think that what we are doing in an optimization is taking data points. As you can see just some points in the room. This is exactly what we can see on the right side, like for this wheel carrier of a Formula Student part. Data is just taking the geometry. It's just taking where are things attached, where is material allowed, where is no material allowed. But from this, you don't get a good design. You need as well some information. Information is the load, the constraints, all of these things that make the material get alive, get a working part. The combination of data and information, this is what an engineer does every day. This is what he's doing in his mind. He takes the geometry data, puts in his information, what he knows about the part, where it is used, and all the additional steps like the post-processing, the manufacturing itself, and some purposes, how long shall the part be in place, etc. All of this, the engineer takes in. But now we add the knowledge as well. Knowledge is what the FEM does. The FEM calculates the internal stresses, displacements, etc. It's connecting the data and the information to get knowledge. And when we now put generative design on top of this, we get creativity. So we say, take the data, take information, take the knowledge of FEM, put all of this together, wrap it up, go for generative design with it, and you get creativity. You get the new designs. And if we get pretty new designs, I already talked about saving weight, saving resources. We are talking about design for sustainability, like reducing weight, reducing material as well for the manufacturing, so reducing waste, like the part on the bottom on the left, we will see later on again. But this example for reducing material, here we can save around 90% waste because it was produced from a big block of material before. But with this pretty good design, we can save a lot of weight in the part and even more waste during the manufacturing. As well, we can reduce production time. Production time, machines, they all take money and resources. So going for lightweight designs, saving production time, and by that, reduce energy. Reduce energy during production and during use. If you have something from the aerospace in mind, bottom left side, there's a satellite technique, or as well the wheel carrier for automotive. If you save weight, save energy during the usage. All of this is driving sustainability. So if I talk about aerospace, manufacturing technologies, automotive, etc., what is this software the right thing for? Where should we use it, and where and who? So there are three hot topics. We have talked about this several times right now. 3D printing at first, lightweighting, saving material, and time efficiency and time to market. I did not cover this topic enough by now, because if you are saving time in the development, not just directly saving money, but you can get your products faster to market. And this will bring you a lot of money. Who? Hot industries? Of course, first 3D printing. So if we have a look at the 3D printing industry market and those who are using semi-effect additive, all of these people are thinking about the perfect designs that are easy to manufacture, that are taking the advantages of 3D printing. Everywhere where you are dealing with 3D printing, there is a need, or at least the possibility to use our software to get better designs. And this can be in the space or aerospace market, in the automotive market, maybe not for mass production. You know that additive manufacturing is more for small or medium batches, but for high performance cars or for individualization, etc., then automotive is there as well. For defense, of course, and for automation. Automation, everything that needs to be moved needs to be lightweight. This is saving time and energy. So robotics, gripper, packaging machines, all of this. We are doing some very good tests with a big packaging machine producer, and we have done a gripper for them, and they have saved a lot of time for the design process, because it's very complex to design these lightweight grippers. But as well, they saved more weight, and the grippers can more easily be moved very fast during the packaging process. Who are we targeting? Of course, designers. I've said this a lot of times. Designers are those who are producing, designing, inventing new parts. So they shall take usage of our software to get the new ideas. But of course, more focused DFAM users, so design for additive manufacturing users. Those that are using additive manufacturing shall have a look at our software. And then hot issues again. So why should we use it? We should overcome aged design thinking, like this is what we have ever done, we will do it again. No, go for new ideas, take the new technology, get new parts. Lengthy design processes, developing step by step again and again, it takes a lot of time to get perfect parts. Go for our software, be faster. Missing expertise for 3D printing. I already mentioned that. Take the new software. If you don't know how to use it best, take our software. Our software will give you designs that are taking the advantages out and that are possible to manufacture. In the end, high effort for optimizations. We have heard this many times. Yes, we do have some parts, might be worth it to have an optimization, but it's so much work. No, don't worry. Just try it out. As well, our software has different shape quality settings. So you can start with a preview setting. You can set up a model in 5 to 10 minutes, maybe not that detailed, so maybe just 2 or 5 minutes, just the most important load cases. And then say shape quality preview, and after 10 to 50 minutes, you see where the design could go to and how much weight can be saved and what could be a result. And if you think, okay, this part seems to be worthwhile, put another 5 to 10 minutes for the details and the loads and the constraints, and run the next setting shape quality balanced. And after 1 or 2 hours, you get your design, and you can think about, I will change some parameters, and by that get to a perfect design that you then run until the end, and you can print it. And of course, lightweight design required. If you have to save weight, take our software and save the weight. No worries, just do it. With this, I'm coming close to the end of my part of the presentation. Afterwards, I will just show you some sample parts, and then Anne will give you a short look at the software itself in a live presentation. But first, I would like to go for a summary of generative design, a new mindset for design. What do we talk about? We talk about efficiency, simplicity, user focus, fostering additive manufacturing, take the advantages of it. We want to get better designs, something that we have in our mind when we have developed the optimization engine. We want to get rid of crappy products. We want to get good designs that are really something that we can be proud of, that these designs are existing. Go for that. Shape the future. Really go for the new things. All of this free from routine. Just doing what you've ever done, you will never get the good designs and really drive the future. So stop routine, start the creativity, and receive innovation. This is what you can do with MSC Apex Generative Design. So see what's possible. Talked about a lot of things, but now let's see about that. This is the wheel carrier we have done for a Formula Student racing team. On the left side, you see how an optimization is running through. This is the results of each iteration just put into a video. So it's nothing faked over there. On the right side, you can see the final design. So I hope that the video streaming is working as well. You can see how the design is detailing step by step, and in the end, you get this final print-ready design. All of this in just 6 hours. Beforehand, this optimization and the design of these wheel carriers in the Formula Student team took around 3, 4, 5, 6 weeks. There's a lot of iterations, designing the result of an optimization, doing again an analysis, seeing, well, this is not a good design, again and again. Now this is fully automated, fully optimized. You get to this print-ready design in just 6 hours. Very incredible. Another thing, this satellite bracket. We have done this in combination with Trumpf, the additive manufacturing machine manufacturer, and Tesat, a satellite manufacturer. It is a part that has been milled before, and they had big issues with distortion and because of internal stresses. So they've come to us and asked, we want to save weight, we want to use additive manufacturing, but we are not sure if it's possible to be printed because of the internal stresses. We are not sure if this would work, but please try it. And we've gone for it, and we have gained 55% weight reduction while reducing the stresses by 30% and increasing the stiffness by 80%. So getting a very lightweight but very strong part. And as I've said already, the designs are made for additive manufacturing. We have put this into the Trumpf machines, printed it, and got out a design that was very, very low distortions, easy to post-process with milling on the interface points, and that was ready. So very good part. Another one, you might have seen already the light hinge that was used by SimuFact for marketing purposes and showing what SimuFact additive can do for the simulation process. EDAC, the design bureau, has gone through this optimization again with our software, and they have gained an overall 70% weight reduction towards the conventional part that is now built in the cars. But they have even gained 40% more lightweight design, so 40% more weight reduction towards the conventional optimization that was used before, and 60% faster than the conventional optimization. So more lightweight and faster than the conventional optimization. And they are very impressed by what you can do, how fast with our software. So this is the last example, just to have a very short glimpse at licensing. We have built several bundles, whatever. You can start with the MSC Apex Generative Design Studio. This is everything you need, and you can work with it, set up models, run optimizations, post-process everything. can get additional GPU licenses, so running the simulation on graphic cards, getting a big increase of speed, and we'll talk about that some slides later. And you could even enhance it with more engines to run several optimizations parallel. Or if you're already a user of MSC1 from other MSC products, you can use as well our software directly with MSC1. And the only thing is you need to activate the usage reporting, but that's everything. If you got a problem, please talk to your sales guys. University bundles are available as well. So if you want to use software, please come to any of your salespeople or to us, and we will take care that you get the right thing out of this. So let's get technical. This is now for Anne. Anne, are you there?
Yes, hello. Thank you for joining the webinar. Before we jump into the software, I just would like to start with some technical suggestions. Thomas already mentioned that we are working on NVIDIA Quadro graphics card to get a faster optimization result. And as you can see on the next slide, we have a performance comparison for that, which shows how much faster you can get with quite good graphics card compared to just CPU calculation. Of course, it's always the question what you want to achieve, and we would suggest you to use, for example, the GPU P4000 because this is a very good graphics card with very good performances, but at a cost that's reasonable. Before we jump into the software, let's go over the workflow of our optimization. First of all, we have the geometry preparation, and this can be done directly in Apex, or you can do this prior in another CAD program and import the CAD data. After this, of course, we need to prepare the geometry and boundary conditions and set this up in different events and do some more optimization setups. For example, put in the stresses. After that, we can just go ahead with the optimization and have a live view in our post-processing. For the result, we just need an intersection to go after the process to have very defined non-design spaces. And of course, if you want to verify the part, you can do a reanalysis with Nastran. This is also possible in a workflow. We are working on a direct workflow for this as well. And you can find some more information on this on our help website, where you can also find more information regarding the background of our optimization algorithms and also some tutorials. Okay, so now I would like to talk a bit about the geometry preparation because it's very easy to transform already existing designs into design spaces for the optimization. As you can see on the left-hand side on the picture, yes, now I can see it at least. I hope you can see it as well. You see a very simple design of a bracket with just 4 screws and another point, fourth entry point. And on the right side, you can see just in a few clicks, I transformed this model into a design space for the optimization. Okay, so now I would like to jump into the software and have a look here. If Thomas is giving me the host. Can you? Oh, okay, so now I'm presenter and I should be able to share my screen. Okay, I hope everyone can see this. I've already prepared this bookshelf prior to this webinar in about 3 minutes. You can see the design is also, it's a very clean and easy design, and I did all of this in Apex. But first of all, I would like to introduce the interface to you. As you can see, it's a very clean and easy to use interface. We just have a few buttons on the right-hand side we need for the geometry setup and for the loads and boundary conditions. And everything we develop or we produce on the right-hand side will be seen here in this tree on the left-hand side. Of course, as I already mentioned, you can also import files. So import the geometry just using these options. And of course, the usual save and export ones and close buttons. Also, you can record videos while setting up the optimization or produce screenshots during your model setup, maybe for some questions later, or if you want to have some photos of the nice results, you can do that as well directly in the software. Okay, now I would like to start with the optimization setup. I already mentioned this is the bookshelf tutorial we usually use. I think you also already saw some results in Thomas's presentation. And I would just go ahead and start the setup with the material definition. First of all, I'm creating a material. Here we just need the Young's modulus, the Poisson ratio as a value, and the density for the mass calculation later on. I will just type these in very quickly, and we can assign the material to the solid. You can see it just popped up here, and you can always have a look which material is assigned to the solid you're using. Next up, we will create our non-design spaces. Probably a lot of you already know this, but in generative design, usually we create non-design spaces and not just put loads directly on surfaces, but on volumes. This is the reason for that is that this method creates better transitions between the non-design and load application points than just using the surfaces. And of course, if you want to do additive manufacturing afterwards, you also want to be able to post-process some of these areas, and therefore you need a bit of material in these areas. As you just saw, you can just click on the volume you want to select, and then on the surface you want to do an offset of, or you can also deactivate this lizard and activate several faces so that they will be created in once. Okay, after defining these non-design spaces, which you can also see on the left-hand side in the model tree, all are here, we create our displacement constraints. For this, we are choosing the cells options because we want to use these just created non-design spaces as our displacement constraint. And we will fix all of them in all directions. Last but not least, we need our force, and we will put 1000 newtons in the negative Z direction and just put it on top of this bookshelf. Okay, now you can see that we've created everything necessary in regards of the boundary conditions and the geometry. But down here on this menu, you can see that we have still some issues actually. We have the help that says that we need to define some more simulation parameters. For this, we are switching to the studies area. In here, you can also see that we have a thumbs down because not all of the information needed for the optimization are put in yet into the model. We can see here our loads and constraints that we defined earlier, and we can click on this if we want to have different events, so different load cases, and we can also activate and deactivate the constraints in here. For this optimization, however, we will just need one event and we will need all forces and constraints in it. Next of all, we will have a look at the generative design settings. Of course, we always want to minimize our mass. This is a given objective of our algorithm, but we can choose between different strut densities and shape qualities. These really influence the design. So they realize the different variations we can create with the software. And last but not least, we will put in our stress goal. And you can see our optimization is now ready to go. We have a thumbs up, and also we have this running man down here with which we can start the optimization. I would like to go to to show you one application setting. It's the Generative Design Solver. In here, you can choose between local solving or remote solving. If you've acquired a license or if you want to calculate on a remote solver, this is possible, and you can just add this in here. Also, you can decide whether you want to optimize on a graphics card or on the CPU. For this simple model, it doesn't make much difference if you calculate on CPU or GPU, but if you have larger models or more higher resolutions, then you want to choose the GPU option according to your license packaging, of course. And the last value I would like to explain is the complexity value. This is a very important value because with this value, our resolution is influenced. So if you choose a higher complexity, your model will have a finer resolution and you will get a more detailed optimization result. But of course, also with a higher resolution, your calculation time will expand and it will take longer to calculate. So for starting with your optimization, I would always suggest using a low complexity value. 14 is a very good one, but you could also go lower if you want to have a really fast, low first peek in how my boundary conditions affect the geometry. And then if you want to have your really detailed, really fine structured optimization result, then I would suggest changing this value. You can sometimes even change it up to 100 depending on your machine capabilities. This is something we are doing quite often with our optimizations. Okay, I will now for this optimization leave it at 14. This is good value for this bookshelf, and I will go ahead and start the optimization. You can see that down below you get the statuses of the optimization. So now it's switching to the post-processing and we are having a live view of the optimization of the run-through. You can see it's going quite fast because of the 14 of the value 14. It's a low resolution, I would say. It's going very fast, and you can see that we've already reduced a lot of material in these first iterations, and the optimization already figured out where a lot of material mainly needs to be, and now the details can be chosen. I will just let this optimization run through and switch to an already prepared model of mine, but we will go back to the other one later. And in here, we can have a look at the post-processing, so at the already done optimizations. Okay, now here you can see a finished design. It's looking very nice. And you can see that we are having a stress plot in the corner, so you can see how the stresses are in the structure. Of course, you might have higher stresses at some boundary limitations, so where the geometry doesn't allow any more material. So the optimization algorithm unfortunately cannot put any more material in this place, but the overall stresses are very homogeneous distributed. And you can also show a mass plot on your right-hand side. You can see this over the iterations, how the mass has reduced significantly till the end. And you can also have a look at your displacements either in a in this fringe plot. Okay, for the post-processing, it's also good to know how to exit it. And you do this over the button here in the down right corner. And you can go ahead and exit your optimization post-process and go back to the model setup. Of course, you can also have a look at all the other optimizations already run through, and you can also switch them directly in the post-processing and change between the already done optimization runs. Okay, now we will switch back to our model we just set up, and we see that we are already at iteration 39. I think for the time's sake, we will stop this iteration, and to show you this as well, you can terminate the simulation up here. And it will take a moment because the iteration will run till the end. And whenever this is finished, the status bar will update just as it happened now. The simulation is terminated. And after it's terminated, you can exit the post-processing. Okay, so with this, I will give the host back to Thomas. And I think we can start with some questions and answering.
Yes, that's right. Thank you, Anne, for showing software. First of all, we have had some sound issues, it seems, at some people. It was clear sound for me, but overall, the webinar is recorded, and we will provide this recording to you, and I hope that the sound will then be good for everybody. There is a question, does optimization process works on an FE solver embedded in Apex or using another software behind, such as Nastran? No, it's not Nastran behind. It's a specific solver for this purpose that is really dedicated to this. It's doing the tasks it should do very fast, but some specific FE things not. So there's no thermal calculation inside or so. So we've left some things out, but we put in always those things that we need for getting the solution. This is really what I was talking about, taking the perfect thing between accuracy and speed. There's direct a question on stresses during optimization, if you can trust to it. More or less, we say the stresses are right, but if you really go for the last grams of weight reduction, or if you have really safety critical parts, we always recommend to use a Nastran verification afterwards to really be sure that the stresses are perfectly and exactly calculated. As well, fitting together with the question before, this is because we are not using the standards for FE calculation, but taking the right things out of it to get a good design fast. But we're not claiming to have a highly accurate stress calculation. I want to combine it with a question elsewhere with a CAD retransition and how to put the optimization of the results into the user's workflow. We are going to integrate, so as this is inside the Apex GUI, and we do have a Nastran simulation in Apex GUI as well. We are going to combine these together, as I said in the slides before as well, combining with other MSC solutions. Step by step, we will do this combination with Nastran first for the verification, but then Adams and SimiFact Additive and Digimet AM. These four are the first on the roadmap. We want to get a one-click solution from getting loads from Adams into Generative Design, and another one-click from getting the design candidate, the result of our optimization, into Nastran and directly copying all the load cases into Nastran, and you will have just one click verify Nastran, and it runs the Nastran verification on a quality and safety level as you expect from a Nastran verification. As well, the export right now is a print-ready, very high-quality STL file. So it's already done. You do not have any issues with that. And as well, we will have very soon a perfect NURBS transition that you can get out a real CAD file that you can work on in your CAD system anywhere else after that. We had the question about manufacturing constraints like overhangs of 45 degrees. No, this is not included. This is a question we very often hear from customers. They are all asking for reducing the amount for support structures. But then we often we had a look at what are the results, how good are the results after doing the real support minimization, and we have seen that this is often taking out too much optimization potential, and the people more want to take into account or accept a little bit more support structure, but having a much better design. We have this on our roadmap, so someone we will develop this manufacturing constraint. But there are other things that we have heard are more important. So if you say this is much more important than anything else, I will take this on the list again that you said it, and that will increase the importance on our side again. So we need your feedback. What do you want us to develop for this software? A direct link to SeamEffect is not already under development. So it's under development, but it's not ready. We're going for this direct combination with SeamEffect in the future. Is it possible to extract optimized geometry? Yes, of course. And could you just click on the open the model again and click on the export button? So it's easy like that. If you want to extract the optimized geometry, you can just click, go to the post-processing panel and say export, and you will get the export. I'm sorry if I miss any questions. If I miss any questions, it's a little bit complicated with chat and Q&As. If I miss anything, or if you want to jump out of the meeting, as we are now at 10 o'clock, you're open to run away, but then just let us know via email later on, and we can answer those questions. So, and please show the export.
I already did. Why you were
sorry.
So the button is down here. I'm sorry, I forgot to mention this one. So export the design candidate. You can choose any iteration you want and just export this iteration into an STL file. Just give it a name. It usually has the name your project is named after. Mine is just Model 5. So at the moment, I would just export it, and I can also choose different parameters. If you want to do a restart later on, which you can find the information for on our help website, please let this stay at meters. Otherwise, you're welcome to choose any other unit you need or want to have, for example, millimeters, and just export it, and it should be in your file.
Okay, so there are a lot of more questions. I think we cannot go through all of them due to the time frame. Just to have a look anywhere, difference towards topology optimization and what is behind there. Yes, of course, behind it is something like topology optimization, but it's based on new approaches. It's not directly evolutionary methods. It's something hybrid. It is not directly following any technology method that is written in the literature by now, but it's close to several, that it's completely different from what you know from a standard topology optimization. We do not have any density-based approach. This is why we can get a geometrical and mechanical feasible result in each iteration. Like this result you can see over here. Of course, it's not perfect, but in fact, it will work and it is a feasible result. Yes, I think we should stop very soon. There's just a very new question of material database. You should always set up your material by yourself, but as Anne has shown, it's mainly important for the optimization. It's just the Young's modulus and the Poisson ratio, and then as well the maximum stresses. This is something that you set up as a goal for the optimization, and mainly, or I've never gone to the perfect to the maximum stresses, but always gone for lower stresses to get a good feasible design. Because if you want to go for the real maximum stress material is capable of carrying, this is mainly much too less material, and as well you will get some durability problems if you go for that critical value. So for aluminium, you have 430, 450 megapascal, and we are mainly optimizing for something like 50 or 60 megapascals, getting much more lightweight designs than before, but having a big safety factor inside and very good lightweight designs. Last question. MSC Apex generative design is based on the platform MSC Apex, but it is a standalone product. So if you already use MSC Apex for structures, for modeler, you need to get this new software as an additional product. And I think with this, we should end the meeting. There are still some questions open. I think we could otherwise prolong this meeting for many hours. So if you really have some questions that we should answer, please just write us an email. And yeah, by that, I would like to thank all of you for your attendance. We will provide the recording, and yes, thank you very much. If you're interested, I'm pretty sure you are interested, otherwise you've not have been here, please contact us or any of our salespeople to get the software and to use it. If you still have some questions, come to us. If you want to us to show what is capable with our software or your specific parts, just reach out to us and we will help you with some benchmark projects and can show you really what is possible. Thank you very much. Bye-bye.